So in the last class, we left off with boron, and we saw that although we predicted boron to have only two ionization energies, an ionization energy related to the electrons in the first shell and an ionization energy related to the electrons in the second shell, we actually saw three different ionization energies. One of those ionization energies was representing the first energy level. I'll represent that with this line here. And then we saw a second that would represent two electrons as well, because the heights are the same. Then we saw a third ionization energy representing only one electron that was a little bit shorter, or that was shorter, because it's representing only one electron. So the first line here represents the first shell. And then the second two lines both represent the second shell. Now the height of this shell here represents two electrons. And this height represents one electron. The main difference is that we have very small difference in ionization energy between these two lines that represented the second shell, whereas we have a very large difference between two different shells. So what this tells us is that our shell model that we had been working with isn't quite right. That it's better for us to speak of these as energy levels, where we may have a range of values. Now, in the first energy level, we really only have the one, but there is only two electrons in that energy level. In the second energy level, we can see that we have slight variation in our energies. We have two electrons that have an ionization energy that's the same, and then that third electron that got added was slightly different. What this represents then for us, and what we're going to introduce as a new concept here, is that we have what's called sublevels. So in our second shell, or second energy level, so it's going to represent the first energy level, and these both will represent the second energy level. With what we call sublevels. This is going to be the S sublevel, and this will be called the P sublevel. So in the second energy level, we have a slight difference with the S sublevel electrons being a little bit harder to remove than what the P sublevel electrons would be. Now let's look how this carries on. So we would call these the 1s, where the 1 represents the energy level, the S represents the sublevel. Every energy level has an S sublevel. And you'll notice here that both of the S's, the first energy level and the second energy level, have the same height. That means they have the same number of electrons. And that also means then that's 2. So at every energy level, we will have what's called an S sublevel, and in that S sublevel, there can only be 2 electrons. Starting with the second energy level, we will have a P sublevel, and we see that here represented, where the 2p represents only 1 electron because it's half the height of the 2s, and the 2s has 2 electrons. Let's look at our next element. We're going to look at carbon. So this time around, I've changed the little notation for the electrons. Instead of using a a solid dot to represent the electron, I've got a tiny little circle to represent the 2 electrons that are going to be part of the p sublevel. So in this diagram here, the 2 electrons at the top, those are going to represent the s sublevel in our second energy level. And these electrons are going to represent our p sublevel electrons. If we go to view or go to predict what this is going to look like in terms of the spectra, we are going to expect to see that our first ionization, or the first energy level's ionization energy, is going to be very high, and we'll have 2 electrons associated with it. We will see that the second ionization, or the second energy level's s sublevel, is also going to have the same height. And now the p sublevel, it'll be a little bit lower in ionization energy, but it too will have the same height. And the reason why is because we have 2 electrons in the first energy level, s. We have 2 electrons in the second energy level, s. And we have 2 electrons in the second energy level, p. So all of the sublevels have equal numbers of electrons. So each one of these represents 2 electrons for our total of 6 electrons total. This is going to represent our 1s, this is going to represent our 2s, and this is going to represent our 2p. Now I just did this rough. Here's the actual diagram to represent that. Now we're going to jump up to neon. And we'll see here now that in our neon we have 10 electrons, and we're going to have 3 different energies. Same as what we expected here for carbon, because we're not done with that p sublevel yet. In fact, if you look at a periodic table, you can see how these, like I said, I think the last time in class, most of the answers are on the periodic table. If you look at the first 2 columns of the periodic table, the reason why there's 2 columns is because those represent electrons in the s sublevel. If we skip over to the boron, carbon, nitrogen, oxygen, fluorine part of the periodic table, those groups are a little bit taller than the middle part. But if you notice, there are 6 of them in a column. So there's 6 columns there, and that would represent the 6 electrons that we can have in a p sublevel. So when we go to do the photoelectron spectrograph for our neon, what we are going to see is, again, we're going to have the first ionization energy representing, or the first energy level electrons represented as high energy, high ionization energy. Now the reason why I drew it a little bit shorter here, so I have enough room to represent the heights correctly. So that's going to be the 1s, and that's going to represent 2 electrons. And then my 2p is going to be the same height. It's going to represent 2 electrons. I'm sorry, 2s. I said 2p. 2s is going to represent 2 electrons. And now, if we go and look at our diagram here, I've got 6 circled electrons, or little circles to represent electrons. So I'm going to have 6 electrons in the p sublevel. And the p sublevel is going to have a little bit less ionization energy than the 2s, but it's also going to be 3 times the height to represent 6 electrons. But that's going to represent the 2p sublevel. And this diagram is going to represent the actual energies associated with this. I'll take the time here to note that when we do these, one of the things to notice is that I've used on each of these that are blank, I've just simply used the same energy scale down at the bottom. But you'll notice here that in our neon, we have extremely high energies compared to what we've been talking about so far. We see that the 1s electrons in our neon require an extremely large amount of energy, close to 100 kilojoules per mole, to remove those electrons from the first energy level. I'm not overly concerned about you getting the actual numbers correct. What I'm more concerned about is that you understand the relative placement and how the energies are changing as we go along. Now, for sodium, we're going to just continue this pattern. We see that we've got an extra electron now in a third energy level. So up to this point, with our neon previously, we had 3 lines, 3 peaks, one representing the 1s, one representing the 2s, and one representing the 2p. And if you look at the periodic table, sodium is in the third row. That now means we have the third energy level. And the very first subshell that we have in any sublevel will be the S. The difference being is that our S in our third energy level is going to require a significantly lower amount of energy to remove that electron compared to the others. So if we were to go through and draw this, and I would tell you, pause this video, draw it out, and then see how I have done it. Okay, you've had the time to go through and draw it out, and here's how I'm going to represent it. I'm going to have the 1s, the first energy level, S sublevel, represented here. It's got 2 electrons. I'm going to have the second energy level represented with 2 electrons. I'm going to have 6 electrons in the P sublevel, so that's going to represent my 2p. And notice that between the first energy level and the second energy level, we have a fairly wide range of values. Okay? Large difference. But within the within the energy level, I got a small difference, because sublevels within the energy level are going to have similar energies. They're not different enough to make it a new shell or new energy level. So my next energy is going to represent the third energy level, and I'm going to have 1 electron there because I've only got 1 electron in the valence shell for sodium, and this is going to be my 3s. So in our electrons, as they get placed into the atoms, they're kind of repetitive. Each energy level is a little bit different, but they also have similarities. So let's look at what sodium would actually look like. And in this case, I've shown it overlaid with neon. So neon being the dark blue, we can see that the 1s, the first energy level S in neon, and the first energy level S in sodium, they have similar they have similar values for their ionization energies, but notice that sodium's higher. Why? Because it has more protons. And with those first energy levels being relatively similar in their distance, the increased number of protons is going to increase that attraction. We see the same things happening with the 2s and the 2p. Sodium, in both instances, is going to have the higher ionization energy for the 2s and 2p electrons because it simply has more protons than what the neon does. But the 1 electron that sodium has in its third energy level is going to be significantly easier to remove than any of the electrons in the second or first energy level from neon. So this is evidence that we are adding energy levels at a significantly different distance further away from the nucleus compared to the sublevels within an energy level. So we're going to skip over to phosphorus now. So we're in the same row on the periodic table. as sodium. We would expect here now an energy for our first energy level is S. We would expect an energy for our second energy level is S. We would expect an energy for our second energy level P, and then we would have a fourth energy for our third energy level S, and then we would have a fifth for our third energy level P. So if we were to draw this out, I'm going to tell you to pause, try it, try placement. Relative placement's good. I'm not overly concerned about the exact numbers. Okay, let's see how you did. So my first energy level, S, 2 electrons. My second energy level, S, 2 electrons. My second energy level, P, 6 electrons, because the P sublevel can hold 6 electrons. My third energy level, S. And then for phosphorus, 1, 2, 3, 4, 5. Is that right? Oh, no, 3. Sorry. 3 electrons in the P. Now, looking at the periodic table, this is going to be something that you could use to help you out. We know where the general area is for these sublevels. The first 2 columns are S's. The 6 taller columns that are grouped 13 through 18, those are P's. And the phosphorus is the third one over, so that means it's going to have 3 electrons in that P sublevel. Actually, I want to change this a little bit because I don't like how far those are away from each other, and that's a little bit better. And here's what it's going to look like. So this will be our phosphorus. For argon, I'm going to take the lazy way out. I'm going to copy these because if you haven't caught on to it yet, it's very repetitive. Oh, guess I don't need to. Oh, I do need to draw it. So I'm going to paste. Nope. Change my mind. Because it's asking us to draw the peaks for the argon with the peaks for phosphorus below. So right now in this diagram, we have phosphorus being shown. What I want you to do now is to draw peaks, and a simple line will be fine. You don't need to try to replicate the little, pretty little picture they've got with the fancy little bottom part. So just draw vertical lines to represent the peaks for argon relative to the peaks with the phosphorus below. Go ahead and pause this and then start it back up once you've got that done. Okay, so let's take a look. Because argon has more protons than the phosphorus does, by 3. It's got 18 versus phosphorus is 15. We are going to have more, we're going to require more energy to remove the electrons for all of these because they're all going to have the same sublevels. It's just the difference is our P sublevel in the third energy is going to have more electrons. So I'm going to draw a relative position here. So that's going to be my neon 1s. This is going to be my neon 2s. This is going to be my neon 2p. This is going to be my neon 3s. I'll get it here in a second. And this is going to be my neon 3p. So if you drew yours so that everything was shifted to the left, because in the left of this, it's a higher ionization energy, then you're good. And the only thing that's going to be primarily different is going to be the height of 3p. So this is our 1s, 2s, 2p, 3s, and 3p. Whereas the 3p for argon has 6 electrons, but the 3p for phosphorus only has 3. Now this is what it would really look like with the actual values. But again, I'm not overly concerned that you get the exact values perfect. I'm looking at, did you get the relative positions correct? Now we're going to talk about calcium, and then we're going to stop here. And then when I'm present, we'll go over how we would do scandium, because scandium is a special situation. So for calcium, if you notice now we have a 4th energy level. We're going to have an energy for the 1s, 2s, 2p, 3s, 3p, and a 4s. So we're going to have a total of 6 vertical lines. I'm going to make the 1s here. I'm going to make the 2s here. I'm going to make the 2p. Three S, 3p, and then 4s. And this is what it would look like with the actual values. So we'll stop there. I will go over with you in class scandium and talk about how the positions on the periodic table can be identified a little bit better, and continue from there. Have a good day, and I will see you on Friday.